Every morning when the first light touches rooftops, water, and streets that are still quiet, we are looking at a star. It is the sun, a celestial body so familiar that we sometimes forget that behind its gentle glow lies an immense sphere of plasma, large enough to contain more than 1,000,000 Earths. The sun does not burn like an ordinary flame. In its core, hydrogen is continuously fused into helium, releasing the energy that has sustained its light for billions of years. Only a tiny fraction of that energy reaches Earth, yet it is enough to warm the oceans, generate wind and rain, nourish plants, drive most of the climate system, and keep life alive. Yet the sun is not a perfectly steady lamp. Beneath its familiar appearance are moving currents of plasma, sunspots, twisted magnetic fields, flares, and clouds of matter that can race through space and affect satellites, communications, and electrical grids on Earth. Even today, many questions about the corona, the solar wind, and the sun's activity cycle remain only partly answered. To understand the star that is bound to the rhythm of day and night and that opened the way for life, we must leave the ground in our imagination, view the solar system from the outside, and then travel step by step from the sun's hottest center to the outer atmosphere that gradually fades into space. At the center of the solar system is the Sun, an object about 333,000 times more massive than Earth and containing roughly 99.86% of the system's total mass. Jupiter is the largest planet, but even Jupiter holds only a tiny fraction compared with the star at the center. This enormous mass creates the gravitational field that keeps Mercury in its close orbit, holds Neptune at a vast distance, and allows comets from the cold, dark outer regions to return after tens, hundreds, or thousands of years. Although we often say that the planets orbit the center of the Sun, the real motion is slightly more subtle. The Sun and the planets all move around the common center of mass of the solar system. Because of the influence of the giant planets, especially Jupiter and Saturn, this center of mass sometimes lies inside the Sun and sometimes just beyond its visible surface. The Sun therefore makes a small motion of its own, rather like an adult spinning with a child, while both move around a point between them. Because the Sun is vastly more massive than the planets, however, its motion around the center of mass is much smaller than the planet's broad orbits. If we continue moving farther away, the entire solar system begins to look like a single point of light in a vast region of space. The Sun is not stationary within the Milky Way. It lies in a minor structure usually called the Orion Spur, or Orion Arm, about 26,000 light-years from the galactic center. The center of the Milky Way is a dense region of stars, gas, and dust, and it also contains a supermassive black hole. The Sun is not close to that turbulent region. It occupies a comparatively quieter area between the galaxy's major spiral arms. The Sun and all the planets are orbiting the center of the Milky Way at hundreds of kilometers per second. Although that is far faster than any vehicle humans have built, the orbit is so vast that the Sun needs more than 200 million years to complete one revolution around the galactic center. Such a revolution is sometimes called a galactic year. Since the Sun formed, it has completed only about 20 orbits of the Milky Way. When the earliest dinosaurs appeared on Earth, the solar system occupied a different position along its galactic path. As future continents continue to change and life evolves in unpredictable ways, the Sun will also move slowly through other regions of the galaxy. In this larger picture, the Sun is only one of hundreds of billions of stars in the Milky Way. It is not the largest, brightest, hottest, or most common star. Most stars in the galaxy are red dwarfs, smaller and dimmer than the Sun. Some stars are tens of times more massive, and some have radii so large that if placed where the Sun is, they would engulf the orbits of several inner planets. Some stars are so hot that their light appears blue-white. Others are faint and cool, emitting most of their energy in infrared wavelengths that human eyes cannot see. The Sun is classified as a G2V star. This designation describes its temperature, spectral color, and the fact that it is in the stable phase known as the main sequence. The Sun is often called a yellow dwarf, although if it were viewed from space without Earth's atmosphere altering its color, its combined light would appear closer to white. Near the horizon, sunlight passes through a thicker layer of atmosphere, which scatters blue wavelengths more strongly and leaves behind yellow, orange, or red light. The color of the Sun as we see it, therefore, depends not only on the star itself, but also on the atmosphere surrounding the observer. The average distance from Earth to the Sun is nearly 150 million kilometers. This distance is used as the astronomical unit, a convenient measure for describing the scale of the solar system. Light travels at almost 300,000 kilometers per second, yet it still takes about 8 minutes and 20 seconds to travel from the Sun to Earth. This means that when we look at the Sun, we do not see it exactly as it is now, but as it was more than 8 minutes earlier. The Sun we know today has existed for about 4.6 billion years. To understand its birth, we must return to a time when many generations of stars had already lived and died within the Milky Way. Older stars had produced heavier elements in their cores and then scattered that material into space through stellar winds or enormous explosions. Hydrogen and helium from the early universe still formed the main ingredients, but they were now mixed with carbon, oxygen, silicon, iron, and many other elements. Matter recycled from those earlier stars would later become the Sun, the planets, rocks, water, air, and living bodies. The Sun was probably born inside a cold molecular cloud of interstellar gas and dust. Clouds of this kind can extend across many light years. Most of their volume is extremely diffuse by earthly standards, but low temperatures allow molecules to survive and gravity to pull matter gradually closer together. Some disturbance likely caused one region of the cloud to begin collapsing. The trigger may have been a shock wave from a nearby massive star exploding, compression associated with motion through a spiral arm of the galaxy, or simply a gravitational instability that developed within the cloud itself. Scientists continue to study chemical traces in meteorites in order to understand the exact environment in which the solar system formed. As one region of gas began to collapse, gravity drew more and more matter toward the center. Conservation of angular momentum caused the cloud to rotate faster as it shrank, much as a figure skater spins more rapidly when pulling in their arms. The material did not fall directly into the center, but gradually formed a flattened, rotating disk. Density and temperature rose at the center of that disk, creating a protostar. Around the protostar lay a protoplanetary disk where tiny grains of dust collided, stuck together, and slowly grew into larger objects. During this early stage, the Sun was not yet a fully formed star. It shone mainly because matter was being compressed, and gravitational potential energy was being released as heat. Gas continued to fall inward, while magnetic fields and rotation produced jets of material directed along the axis. As the young Sun accumulated most of its final mass, its core became steadily hotter and denser. Eventually, the temperature crossed the threshold at which hydrogen nuclei could begin to fuse. From the moment nuclear fusion became its primary source of energy, the Sun entered the main sequence stage. Within the surrounding disk, dust grains containing metals and minerals could survive close to the Sun, where temperatures were high. Farther out, in colder regions, water and many volatile compounds froze, creating a larger supply of solid material. This difference helps explain why the inner planets, Mercury, Venus, Earth, and Mars, became primarily rocky worlds, while the outer planets were able to accumulate much greater amounts of gas and ice. Jupiter and Saturn formed quickly enough to capture large quantities of hydrogen and helium before the remaining gas in the disk was blown away by the young Sun's wind. The formation of the solar system was not peaceful. Young bodies collided, changed orbits, and were sometimes thrown out of the system entirely. Earth most likely struck another young planet, producing material that later gathered together to form the Moon. The giant planets are thought to have migrated away from their original birthplaces, disturbing the orbits of smaller bodies. Comets and asteroids transported material from different regions and helped deliver volatile compounds to the rocky planets. Impact craters on the Moon and on worlds without atmospheres still preserve traces of that violent era. The young Sun was also more active than it is today. It rotated faster, possessed a more intense magnetic field, and produced more high-energy radiation. Its stellar wind swept through the protoplanetary disk, driving away the remaining gas and bringing the main phase of planet formation to an end. Over time, major collisions became less frequent. Orbits gradually settled, though they never became perfectly unchanging. From a cold cloud in space, a planetary system emerged, with a star at its center, and at least one world where conditions eventually allowed life to arise. By measuring the ages of the oldest meteorites, especially calcium and aluminum-rich inclusions, regarded as some of the first solids to condense in the solar system, scientists can estimate when this process began. These samples are like the opening pages that remain from a book whose greater part has been lost. They do not tell the whole story, but the isotopes within them allow their ages to be determined with remarkable precision. From this evidence, we know that the Sun and the planets belong to a single family that formed about 4.5 to 4.6 billion years ago. Today, the Sun has a diameter of about 1,390,000 kilometers. A line of roughly 109 Earths would stretch across it from one side to the other. In terms of volume, more than 1 million Earths could fit inside the sphere of the Sun, although real spheres cannot be packed together without leaving empty spaces. The Sun's mass is about 2 times 10 to the 30th kilograms, a number so large that it is difficult to connect with ordinary experience. Even so, the Sun is still a star of only moderate mass, not massive enough to end its life in a supernova explosion. The Sun's average density is much lower than Earth's. This may seem surprising because the solar core is under immense pressure, but most of the star's volume lies in its outer layers where matter is far less dense. The Sun is not an ordinary ball of gas. At very high temperatures, electrons are stripped away from atomic nuclei, producing plasma. Plasma conducts electricity, responds to magnetic fields, and creates many of the phenomena visible on the Sun's surface and throughout its atmosphere. Gravity at the Sun's visible surface is about 28 times stronger than gravity on Earth. No person could stand on the Sun because there is no solid ground and the heat would destroy every familiar material. But if we imagined a safe surface, the weight of a human body would be far beyond what it could endure. The escape velocity at the solar surface is also greater than 600 kilometers per second. Even so, particles in the solar wind are able to leave because they are accelerated in the hot corona and are driven by pressure, waves, and magnetic fields. The Sun does not rotate like a solid sphere. Its equatorial region completes a rotation faster than the regions near the poles. By tracking features in the photosphere, astronomers find that the equator turns once in nearly 25 days, while high-latitude regions require more than 30 days. Measurements made from Earth are also affected by our planet's own orbital motion. This differential rotation plays an important role in stretching and twisting magnetic field lines and helps produce the Sun's cycle of activity. About 3/4 of the Sun's mass is hydrogen, and nearly 1/4 is helium. Other elements, including oxygen, carbon, neon, iron, nitrogen, silicon, magnesium, and sulfur, make up only a small fraction. In astronomy, all elements heavier than hydrogen and helium are commonly called metals, even though many of them are not metals in the chemical sense. The metallicity of a star helps scientists understand the environment in which it formed and compare it with stars from other generations. The temperature of the photosphere, the layer our eyes usually regard as the sun's surface, is about 5,800 Kelvin. In the core, the temperature reaches roughly 15 million Kelvin, but temperature does not simply decrease from the center outward. Above the photosphere and chromosphere, it rises sharply through the transition region and reaches millions of Kelvin in the corona. This reversal creates one of the most famous problems in solar physics. Why is the atmosphere far from the fusion-powered core so much hotter than the visible surface below it? Every second, the sun radiates about 3.8 times 10 to the 26th watts of power. Written in full, the number would contain 27 digits. Only a tiny fraction of the energy spreading in all directions passes through Earth. At our orbital distance, a surface placed perpendicular to the sunlight outside, the atmosphere receives about 1,360 watts per square meter. Because Earth is spherical, rotates, and reflects part of the incoming light, the average amount absorbed across the whole planet is much lower. Even so, that small share is enough to drive almost the entire climate and biological system of Earth. The sun's brightness is relatively stable over the scale of a human lifetime, but it is not perfectly constant. Its total output changes slightly with the magnetic activity cycle. Darker sunspots reduce the light emerging from certain regions, while bright areas called faculae often compensate for that reduction and can even make the sun's total brightness rise slightly during active periods. The variation is small, but modern instruments can measure it. Over billions of years, the change in brightness is much greater because the composition of the core slowly evolves. The sun exists in a state of relative balance between two opposing tendencies. Gravity pulls all matter inward and tries to make the star contract. Pressure from hot gas and radiation pushes outward. When these forces balance, the sun maintains a fairly stable size. This condition is known as hydrostatic equilibrium. If fusion in the core suddenly weakened, pressure would fall and gravity would compress the core. That contraction would raise the temperature and strengthen the reactions. If too much energy were produced, the star would expand, the core would cool, and the reaction rate would slow. This feedback mechanism allows main sequence stars to remain stable for extremely long periods. Although diagrams often divide the sun into clearly defined layers, the real boundaries between them are not like divisions in a solid object. Temperature, density, pressure, and the way energy is transported change gradually with distance from the center. Even so, dividing the sun into the core, radiative zone, convective zone, and atmospheric layers helps us understand the different processes that dominate each region. The core occupies roughly the innermost quarter of the sun's radius, yet it contains a substantial share of the star's mass because its density is so high. This is where nuclear fusion occurs rapidly enough to supply almost all the sun's energy. At the center, pressure reaches hundreds of billions of times the atmospheric pressure at Earth's surface. Protons move rapidly through the hot plasma, but because they all carry positive electric charge, they repel one another. According to classical physics, most protons do not have enough energy to overcome this electrical barrier and approach closely enough for the strong nuclear force to bind them. Quantum mechanics allows a small fraction of particles to tunnel through the barrier. Because countless collisions occur continuously, the total number of successful reactions is still enough to sustain the sun's luminosity. Outside the core lies the radiative zone. Here the plasma is too dense for large-scale convection to transport energy efficiently. Energy moves outward mainly through radiation. A photon, however, does not simply fly in a straight line from the core to the surface. It is repeatedly absorbed and re-emitted or scattered by particles. Each step may be very short and its direction nearly random. As a result, although light crosses interplanetary space very quickly, energy created in the core may need tens of thousands to hundreds of thousands of years to pass through the Sun's interior. During this process, the original photon does not preserve its identity. Energy is absorbed, transferred, and re-emitted many times at different wavelengths. Saying that a photon takes hundreds of thousands of years to escape is only a simplification. More accurately, the original energy passes through a complex chain of interactions before finally emerging at the surface as visible light, infrared, ultraviolet, and other forms of radiation. The sunlight entering a window today may carry energy that began to be released before ancient human populations had appeared, or while the first civilizations still lay far in the future. Near the outer boundary of the radiative zone is a transition layer called the tachocline. This is where the nearly solid body rotation of the deeper interior gives way to the stronger differential rotation of the convective zone. The tachocline is thought to be important in the mechanism that generates the Sun's global magnetic field. Electrically conducting plasma moving inside a rotating star can act like a natural dynamo. Exactly how flows in the tachocline and convective zone combine to produce the magnetic cycle, however, remains a major subject of research. Beyond the radiative zone lies the convective zone, extending from about 70% of the Sun's radius to the photosphere. Here, lower temperatures make the plasma more opaque to radiation. Photons alone can no longer carry energy outward efficiently, so hot material rises, releases heat, cools, and sinks again. The process resembles boiling water, but it takes place in plasma and on vastly larger scales. At the photosphere, convection appears as bright cells called granules. Each granule is roughly 1,000 kilometers across, comparable to the distance between many cities on Earth. The brighter center marks where hot plasma rises. The darker edges are where cooler material sinks. These structures change within only a few minutes, making the solar surface look as though it is gently boiling when observed with a high-resolution telescope. Beyond individual granules are larger convective patterns, including supergranules that extend across tens of thousands of kilometers. Plasma motions carry small magnetic fields toward the edges of these large cells and help create a network of magnetism across the surface. In processed images viewed at low resolution, the Sun may appear comparatively smooth. At high resolution, however, it becomes a constantly changing landscape of flows, plasma columns, dark patches, and magnetic threads that are continually being rearranged. Humans cannot send an instrument deep inside the Sun, yet its interior can be studied through a method similar to the way seismology probes the inside of Earth. The Sun is constantly vibrating. Sound waves travel through its internal layers, reflect, and create millions of oscillation modes at the surface. By measuring tiny movements in the solar atmosphere, scientists can infer the speed of sound, rotation, and structure at different depths. And this field is known as helioseismology. Helioseismology shows that the Sun's interior rotates differently from its outer layers and helps locate the boundary between the radiative and convective zones. It also allows researchers to study large-scale flows connected with the activity cycle. Because sound waves pass through the whole star, active regions on the far side can even be detected before they rotate into view from Earth. This supports space weather forecasting, although the accuracy of such forecasts remains limited. Another messenger that comes directly from the core is the neutrino. These particles interact so weakly with matter that they pass through almost the entire Sun without being stopped. While radiant energy takes an extremely long time to reach the surface, neutrinos leave the core and arrive at Earth in a little more than 8 minutes. They carry nearly immediate information about fusion reactions. Because neutrinos interact so rarely, however, detecting them requires enormous instruments placed deep underground, beneath mountains or within ice, in order to reduce interference from other particles. After energy has crossed the interior, it reaches the layer we usually call the Sun's surface. But the Sun has no solid surface like Earth. The photosphere is simply the depth at which the plasma changes from relatively opaque to transparent enough for photons to escape into space. Below it, light is continually absorbed and scattered by matter. Above it, the density becomes low enough for a large fraction of photons to escape. Our eyes therefore perceive a fairly sharp boundary, even though matter continues beyond it. The photosphere is only a few hundred kilometers thick, extremely thin compared with the Sun's radius of nearly 700,000 kilometers. Temperature decreases upward through this layer, so the higher regions are generally cooler. When we look toward the center of the solar disk, we see deeper into hotter material. Near the edge, our line of sight passes diagonally through higher, cooler layers, making the rim appear darker. This effect is called limb darkening, and it is evidence that the solar atmosphere changes with depth. The spectrum of sunlight is not a perfectly continuous band of color. Against the rainbow background are thousands of dark lines where atoms and ions in the solar atmosphere absorb particular wavelengths. These are known as Fraunhofer lines. Every element leaves its own pattern, much like a fingerprint. By studying the positions, widths, and strengths of these lines, scientists can determine the chemical composition, temperature, pressure, motion, and magnetic field of the plasma without collecting a physical sample. Immediately above the photosphere lies the chromosphere. In ordinary light, it is hidden by the much greater brightness of the photosphere. During a total solar eclipse, it briefly appears as a thin red rim around the Sun. Its distinctive red color is associated with hydrogen radiation at a particular wavelength. When observed through a hydrogen alpha filter, the chromosphere becomes a world of long filaments, bright regions, and complex moving structures. Within the chromosphere, narrow columns of plasma called spicules rise at high speed. Each spicule survives only a short time but can extend thousands of kilometers upward. Because enormous numbers of them appear across the Sun, they may help transport energy and matter into the upper atmosphere. Measuring them and understanding how they form is difficult, however, because they are small, move rapidly, and overlap one another along the observer's line of sight. The temperature of the chromosphere initially continues to fall above the photosphere, reaches a minimum temperature region, and then begins to rise. Higher still is the transition region, where the temperature jumps from tens of thousands to hundreds of thousands or even millions of Kelvin across a comparatively short distance. This region is not a smooth, flat layer. Magnetic loops, plasma flows, and dynamic structures below it bend, raise, and lower its shape. Beyond the transition region lies the corona, the Sun's outermost atmosphere. During a total solar eclipse, when the Moon covers the photosphere almost exactly, the corona appears as a pearly white glow extending far outward. Its shape changes with the activity cycle. When the Sun is quiet, long structures may be concentrated near the equator, and coronal holes appear near the poles. During active periods, the corona becomes more complex, with streamers spreading in many directions. The corona is extremely hot, but very thin. Particle temperatures reach 1 to several million Kelvin and can rise still higher in active regions. Even so, an object placed there would not receive heat in the same way it would from dense matter at the same temperature, because there are so few particles in each unit of volume. In physics, temperature describes the average kinetic energy of particles, while the sensation and transfer of heat also depend on density and the rate at which energy is delivered. The question of why the corona is hotter than the photosphere has remained open for decades. Energy must be carried upward from the lower layers, perhaps through magneto-hydrodynamic waves that travel along magnetic fields, or through countless small magnetic reconnection events, sometimes called nanoflares. Observations indicate that both waves and reconnection contribute, but their relative importance in different regions is still being investigated. There may be no single mechanism that explains coronal heating everywhere. The bright loops seen by ultraviolet telescopes are hot plasma confined along magnetic field lines. Electrically charged matter does not move easily across a strong magnetic field, so it follows curved paths that rise from the surface and return again. These loops can be thousands of kilometers wide and tens of thousands of kilometers long. Some remain relatively stable, while others change rapidly or take part in explosive events. Dark regions in X-ray and ultraviolet images are called coronal holes. They are not true empty holes, but areas where the plasma is less dense and cooler than its surroundings. Here, magnetic field lines open into space instead of closing back near the surface. Plasma escapes more easily and produces high-speed streams of solar wind. When a coronal hole rotates into a position facing Earth, the fast stream may arrive several days later and disturb the planet's magnetic environment. Farther outward, the corona gradually becomes the solar wind. There is no sharp boundary where the Sun's atmosphere suddenly ends. Matter from the star continually expands throughout the solar system, carrying magnetic fields with it and creating an immense region of influence. In this sense, Earth and the other planets move within the Sun's extended outer atmosphere. The energy that sustains all of these layers begins with nuclear fusion in the core. The main mechanism is the proton-proton chain, in which 4 protons are ultimately converted into one helium-4 nucleus. The product has slightly less mass than the original particles. The difference appears as energy, while the reactions also produce positrons, neutrinos, and photons. The first step is especially slow because one of 2 protons must transform into a neutron through the weak nuclear force. This slowness is the reason the Sun can remain stable for billions of years. If hydrogen fused too easily, the star would consume its fuel far more quickly and could not maintain a long-lasting stable environment for its planets. Other reaction cycles dominate in larger and hotter stars, but in the Sun the proton-proton chain produces most of the energy. In the most common branch of the proton-proton chain, 2 protons interact and one changes into a neutron through the weak force, creating deuterium, a positron, and an electron neutrino. The deuterium nucleus quickly captures another proton to form helium-3 and emits a gamma-ray photon. Finally, 2 helium-3 nuclei combine to form helium-4 and release 2 protons back into the plasma. Those returned protons can then participate in other reactions. The proton-proton chain also has less common branches involving helium-3, helium-4, beryllium, and boron. Each branch produces neutrinos with different energies. By measuring the neutrino spectrum arriving at Earth, scientists can test the temperature of the core and the relative rates of different reactions without directly observing the center of the Sun. Alongside the proton-proton chain, the Sun also operates the carbon-nitrogen-oxygen cycle. In this cycle, nuclei of carbon, nitrogen, and oxygen act as catalysts that help convert hydrogen into helium. The Sun's core is not hot enough for this mechanism to dominate, so it contributes only a small fraction of the total energy. In more massive and hotter stars, the carbon-nitrogen-oxygen cycle becomes the principal source of power. Every second, the Sun converts hundreds of millions of tons of hydrogen into helium. The helium products have slightly less mass than the original protons. The difference, several million tons each second, is transformed into energy according to the famous relationship between mass and energy. The amount sounds immense, but compared with the Sun's total mass, the loss each second is tiny. even after billions of years, the Sun still retains most of the mass with which it began. Saying that the Sun is burning can be misleading if it suggests fire on Earth. An ordinary flame is a chemical reaction between matter and oxygen that rearranges electrons around atoms. Fusion changes the atomic nuclei themselves and releases vastly more energy per unit of mass. The Sun does not need oxygen, contains no wood or chemical fuel, and cannot be extinguished by removing air. The rate of energy production per cubic meter through most of the core is not as intense as the image of a furious reactor might suggest. The total power becomes enormous because the core occupies such a vast volume. A small volume of the core produces energy at a rate not radically different from some biological or ordinary thermal processes. What is extraordinary is not that every cubic meter releases energy with extreme violence, but that a region hundreds of thousands of kilometers across continues these reactions for billions of years. The released energy initially appears mainly as high-energy radiation and particle motion. As it passes through the dense layers, it is absorbed and re-emitted many times, gradually becoming lower-energy photons. After its long journey, a photon escapes the photosphere and travels into space. A photon moving in Earth's direction takes a little more than 8 minutes to reach the atmosphere, where it may be reflected, scattered, or absorbed. Some photons are absorbed by ozone, especially in the dangerous ultraviolet range. Some create the blue sky when they are scattered by molecules in the air. Some strike leaves and take part in photosynthesis. Some warm the ground, water, and atmosphere. Some enter the retina and become images in conscious experience. Energy that began in nuclear reactions deep inside the Sun eventually helps create the motion of wind, the flow of rivers, a cloud, a grain of rice, or warmth on the skin. Neutrinos follow a different path. They are barely obstructed and travel almost directly out of the core. For much of the 20th century, experiments detected fewer solar neutrinos than theoretical models predicted. The discrepancy led scientists to ask whether the models of the Sun were wrong. Eventually, physicists discovered that neutrinos can change from one type or flavor into another as they travel. Early detectors were sensitive to only one flavor and therefore missed the others. Solving the solar neutrino problem both confirmed the model of fusion inside the Sun and showed that neutrinos have mass, although only a very small amount. While the core provides a steady source of energy, magnetic fields create much of the Sun's changing and sometimes violent appearance. Electrically conducting plasma moving within the rotating star produces electric currents. Those currents generate magnetic fields, and the magnetic fields in turn influence the motion of the plasma. This feedback system is known as the solar dynamo, because the flows are extremely complex, simulating the entire magnetic field from the deep interior to the atmosphere remains a major challenge. A simple bar magnet has 2 poles and a comparatively stable field. The Sun's magnetic field is far more complicated. On the largest scale, it may resemble a dipole during periods of low activity, but the photosphere contains countless smaller magnetic regions with positive and negative polarities lying beside one another and field lines being stretched or twisted. Differential rotation moves the equatorial region faster than the polar regions and wins the magnetic field around the star. Meridional circulation slowly carries plasma and magnetic flux from the equatorial regions toward the poles along the surface. The return flow in deeper layers is still being studied. Together with convection and differential rotation, this motion helps weaken the old magnetic field, reverse the field at the poles, and prepare the Sun for the next cycle. Sunspot groups often appear in pairs with opposite magnetic polarities, like the 2 ends of a magnetic loop rising through the convective zone. Hale's law describes how the leading and trailing polarities of these sunspot pairs are opposite in the northern and southern hemispheres, and then reverse their order in the following cycle. The roughly 11-year sunspot cycle is therefore only half of a complete magnetic cycle, lasting about 22 years. Sunspots are regions where strong magnetic fields pass through the photosphere. The magnetic field suppresses convection, so energy from below is not transported upward as efficiently as it is in surrounding areas. Sunspots are therefore cooler and darker. They still have temperatures of thousands of Kelvin and would shine brilliantly if seen apart from the sun. They appear black only because they lie beside the hotter and brighter photosphere. A single sunspot may be smaller than Earth, while large groups can stretch across hundreds of thousands of kilometers. Through a telescope, a sunspot usually has a dark central region called the umbra and a brighter filamented outer region called the penumbra. The magnetic field in the umbra tends to be more vertical, while in the penumbra it is more inclined and produces complex plasma flows. Sunspots may last for hours, days, or weeks, changing shape as the sun rotates. The number of sunspots rises and falls in a cycle averaging about 11 years. At the beginning of a cycle, sunspots generally appear at middle latitudes. As time passes, the active zones gradually move toward the equator. When their positions are plotted over time, the pattern forms bands resembling butterfly wings. Near solar maximum, active regions, flares and eruptions become more common. Near solar minimum, the surface may remain free of sunspots for days or even weeks. No cycle repeats the previous one exactly. Some are strong and others weak, their lengths differ, and activity in the two hemispheres is not always synchronized. Solar maximum may be prolonged or may appear as two separate peaks, showing that the solar dynamo behaves as a changing system rather than a perfect clock. From the middle of the 17th century to the early 18th century, very few sunspots were recorded during a period known as the Maunder minimum. This interval overlapped with part of a cooler climatic period in many regions of the northern hemisphere, but the relationship was not simple and the sun was not the only influence. Volcanoes, oceans, greenhouse gases, and the climate system's internal variability all played roles. Studying periods of low solar activity helps scientists understand the natural range of solar change, but these periods cannot be used to replace other explanations of climate behavior. Alongside sunspots are bright regions known as plages and faculae. They are associated with concentrated magnetic fields and often surround active regions. Faculae are especially easy to see near the edge of the solar disk, where the structure of the atmosphere allows deeper, hotter layers to become visible. During periods with many sunspots, the brightness of faculae usually more than compensates for the darkening caused by the spots, so the sun's total radiation increases slightly. In the chromosphere and corona, magnetic fields support long structures of plasma called filaments when seen against the solar disk and prominences when seen at the edge. They may extend for hundreds of thousands of kilometers and survive for days or weeks. Relatively cool, dense plasma is suspended within the hot atmosphere by magnetic structures. When those structures become unstable, a prominence may erupt into space or take part in a coronal mass ejection. Solar flares occur when magnetic energy is released suddenly, usually through magnetic reconnection. Field lines in the plasma can be stretched, twisted, and pressed together. When their configuration changes, stored energy is converted into heat, plasma motion, and particle acceleration. Within minutes, a small region of the sun may brighten intensely in X-rays and ultraviolet light and release an enormous amount of energy. Flares are classified by their X-ray intensity, usually in the categories A, B, C, M, and X. Each class is about 10 times stronger than the one before it, while X-class events receive additional numbers to indicate intensities above the basic threshold. This classification is useful, but it does not tell the whole story. The effect on Earth also depends on where the flare occurs, the direction of energetic particles, and whether the event is accompanied by an eruption of matter. Electromagnetic radiation from a flare travels at the speed of light, and therefore reaches Earth after a little more than 8 minutes. Strong X-rays and ultraviolet radiation alter the ionosphere on the daylight side of the planet and can disrupt high-frequency radio communication. Energetic particles arrive tens of minutes or several hours later, and, if the event is powerful enough, can threaten satellites, astronauts, and aircraft flying over polar regions. A coronal mass ejection, usually abbreviated as CME, is an enormous cloud of plasma and magnetic field expelled from the corona. A CME may carry billions of tons of matter and travel at speeds ranging from a few hundred to more than 2,000 kilometers per second. Not every CME is directed toward Earth. When viewed head-on, an eruption coming straight toward us may appear as an expanding halo around the occulting disk of a coronagraph. Three phenomena that often occur together must be distinguished from one another. A solar flare is primarily a sudden increase in electromagnetic radiation. A coronal mass ejection is a cloud of plasma and magnetic field thrown outward. The third category is solar energetic particles, protons, electrons, and ions accelerated rapidly near a reconnection region or at a shockwave driven by an eruption. The fastest of these particles can reach the region around Earth within tens of minutes, creating hazards for astronauts, satellites, and polar flights. When a CME approaches Earth, the orientation of the magnetic field inside it becomes especially important. If that field points opposite to Earth's field on the daylight side, magnetic reconnection can occur efficiently and allow much more energy to enter the magnetosphere. The result is a geomagnetic storm with strong electric currents flowing through the magnetosphere and ionosphere. Auroras may spread to latitudes much lower than usual, forming green, red, or violet curtains of light across the sky. Auroras are among the most beautiful expressions of the connection between the Sun and Earth. Particles are guided along magnetic field lines toward the polar regions, where they collide with atoms and molecules in the atmosphere. Oxygen emits green or red light, while nitrogen contributes blue and violet. Each color is associated with different altitudes, particles, and collision energies. The quiet display overhead is actually the visible trace of a process that began with magnetic activity on the Sun. Geomagnetic storms, however, do more than create beautiful skies. Changing electric currents in space can induce currents in long power lines, pipelines, and cables. In 1859, a powerful event now known as the Carrington event produced auroras far from the poles and caused some telegraph systems to behave abnormally. In 1989, a geomagnetic storm contributed to a power grid failure in Quebec that lasted for hours. Modern society depends on satellites, navigation, communication, and electrical networks, making space weather forecasting increasingly important. The solar wind exists even when there are no flares or CMEs. It is a continuous stream of plasma escaping from the corona, made mainly of protons, electrons, and helium nuclei. The slow solar wind usually travels at a few hundred kilometers per second, while fast wind from coronal holes can reach 700 or 800 kilometers per second. Because the Sun rotates, the wind draws the magnetic field outward into a spiral pattern known as the Parker spiral, rather like water sprayed from a rotating sprinkler. The exact mechanism that accelerates the solar wind is still not completely understood. The corona is hot enough for plasma to expand outward, but observations show that waves, turbulence, and magnetic reconnection also supply energy. Fast and slow solar wind have different origins. Fast wind is generally associated with open magnetic field regions, while slow wind probably emerges from the boundaries of coronal holes, from areas with complex magnetic structure, or from plasma released when magnetic loops rearrange. When fast solar wind catches up with slower wind emitted earlier, the two form a correlating interaction region. Because the source structure rotates with the Sun, the disturbed region can sweep past Earth at intervals close to the Sun's rotation period. These regions often produce mild or moderate geomagnetic storms that last longer than the sudden effects of a CME. During periods of low solar activity, long-lived coronal holes can cause disturbances to repeat over several rotations. The solar wind and its magnetic field carve out an enormous bubble in the interstellar medium. This bubble is called the heliosphere. It surrounds all the planets and extends far beyond the orbit of Neptune. Within the heliosphere, conditions in space are influenced mainly by the Sun. Outside lies the local interstellar medium, containing plasma, magnetic fields, dust, and cosmic rays arriving from more distant sources. As the solar wind travels outward, it expands and slows. At a boundary called the termination shock, its speed falls from supersonic to subsonic relative to the characteristic wave speed in the plasma. Farther out lies the heliosheath, where the wind has slowed and become compressed. Finally, at the heliopause, the pressure of the solar wind balances the pressure of the interstellar medium. The true shape of the heliosphere is complex and need not resemble the simple teardrop with a long tail shown in older illustrations. The two Voyager spacecraft launched in the 1970s have traveled farther than any other human-made probes and crossed the heliopause at different times. They have not escaped the full gravitational domain of the Sun and will require an extremely long time to pass through the hypothetical Oort cloud. Even so, their measurements of changes in plasma density, cosmic rays, and magnetic fields provided the first direct data from the boundary between the heliosphere and interstellar space. The heliosphere reduces the number of high-energy cosmic rays that enter the solar system. When solar activity is strong, enhanced magnetic fields and solar wind block more galactic particles. When activity is weak, more cosmic rays can penetrate inward. Earth receives additional protection from its magnetosphere and atmosphere, but astronauts traveling for long periods to the Moon or Mars would face a much harsher radiation environment. Each planet interacts with the solar wind in its own way. Earth, Jupiter, Saturn, Uranus, and Neptune possess substantial internal magnetic fields that form magnetospheres. Venus lacks a strong global magnetic field, but the solar wind interacts with its ionosphere and creates an induced magnetosphere. Mars retains only localized magnetic regions in its crust. The loss of most of its global field, together with its thin atmosphere, has allowed the solar wind to help strip gases from the planet over long periods. Comets also reveal the Sun's influence. As a comet approaches the star, its ices sublimate and release gas and dust. Radiation pressure pushes the dust into a curved tail, while the solar wind and magnetic field draw ions into a straighter tail. Both tails point away from the Sun, whether the comet is moving inward or outward. A comet may therefore appear to travel in a direction opposite to that of its own tail. Although the Sun influences every planet, its effect on Earth is especially profound because this is where life has developed. Nearly every ecosystem at the surface depends directly or indirectly on sunlight. Plants, algae, and some bacteria use photosynthesis to convert light energy into chemical energy. They combine carbon dioxide with water to produce organic compounds and release oxygen. Animals eat plants or other animals, so the energy moving through most food chains ultimately comes from the Sun. Even coal, oil, and natural gas contain ancient solar energy that living organisms once absorbed and stored in organic matter. Over millions of years, heat and pressure transformed that material into fuel. When humans burn it, the chemical energy is released, but carbon also returns to the atmosphere far more quickly than geological processes once buried it. Not every organism depends directly on light. On the ocean floor, some ecosystems around hydrothermal vents rely on chemosynthesis and obtain energy from chemical reactions. Yet even these environments exist on a planet whose liquid oceans, climate, and geological history have been deeply shaped by the Sun. Life can follow paths that do not require direct sunlight, but Earth's overall conditions remain tied to its position around the star. The Sun heats Earth's surface unevenly. Regions near the equator receive more direct energy, while the polar regions receive sunlight at a lower angle and endure long seasons with little illumination. These temperature differences drive motion in the atmosphere and oceans. Warm air rises and cooler air moves in to replace it, while Earth's rotation deflects the moving currents. From these processes arise wind belts, ocean currents, low and high pressure systems, and many patterns of weather. Solar energy evaporates water from oceans, lakes, rivers, and soil. Water vapor rises, condenses into clouds, and returns to the surface as rain or snow. Water then flows through rivers, seeps into the ground, or freezes before evaporating again. Although terrain, climate, and gravity all shape the water cycle, most of the energy that powers it comes from the Sun. The seasons do not occur because Earth moves slightly closer to or farther from the Sun. Their main cause is the tilt of Earth's rotational axis, about 23.5 degrees relative to the plane of its orbit. When the northern hemisphere tilts toward the Sun, it experiences longer days and more direct sunlight, producing summer, while the southern hemisphere experiences winter. 6 months later, the situation is reversed. Earth's orbit is slightly elliptical, yet the planet is actually closest to the Sun in early January, during winter in the northern hemisphere. Earth's distance places it within a region where liquid water can exist on the surface under suitable atmospheric conditions. Yet there is no simple boundary that determines whether a planet is habitable. Atmospheric composition, pressure, clouds, oceans, reflectivity, and geological activity all matter. Venus and Mars show that worlds whose sizes or locations are not entirely unlike Earth's can still develop along very different paths. Earth's atmosphere retains some heat through the natural greenhouse effect. Water vapor, carbon dioxide, methane, and other gases absorb infrared radiation emitted by the surface. Without this effect, Earth's average temperature would be much lower and most surface water would freeze. When greenhouse gas concentrations increase, however, the energy balance changes and the planet warms. The Sun supplies energy to the climate system, while greenhouse gases influence how much of that energy is retained. Solar activity can have a small influence on climate through changes in radiation and interactions with the upper atmosphere. Measurements of solar brightness, however, do not show an increase large enough to explain the modern trend of global warming. In discussing climate, it is necessary to distinguish variations caused by the Sun, volcanoes, oceans, and changes driven by human activity. The fact that the Sun is the climate system's energy source does not mean that every change in temperature begins with a change in the Sun. In the distant past, the young Sun was only about 70% as bright as it is today. If Earth's atmosphere had then resembled the present one, the oceans would probably have frozen. Geological evidence, however, shows that liquid water existed very early. This puzzle is known as the faint young sun paradox. Proposed solutions involve higher concentrations of greenhouse gases, a different atmospheric composition, clouds, darker surfaces, and combinations of several factors. It illustrates that a planet's habitability depends both on its star and on the planet's own evolving history. Sunlight also has a dangerous side. Ultraviolet radiation can damage biological molecules, harm DNA, and increase the risk of disease. The ozone layer absorbs most high-energy ultraviolet radiation and makes Earth's surface safer. The magnetosphere and atmosphere block many energetic particles from the Sun, but not all of them. Humans and other organisms must live within a balance between the benefits and hazards of sunlight. The Sun also regulates biological rhythms. Many organisms use the cycle of light and darkness to control sleep, waking, feeding, reproduction, and migration. The human body contains a biological clock that responds to light, especially morning light. Before electricity, human life was more closely tied to natural day and night. Artificial lighting now allows activity to continue after sunset, yet our bodies still carry mechanisms that formed under the illumination cycle of a planet rotating around a star. Long before people understood nuclear physics, they recognized the sun's importance. Many cultures imagined it as a god, an eye in the sky, a chariot, a disk of fire, or a source of royal authority. These interpretations were not merely expressions of ignorance. They reflected the observation that harvests, time, warmth, and life depended on a celestial body beyond human control. Ancient structures were aligned with sunrise or sunset at particular times of year. Tracking the changing position of sunrise along the horizon helped identify the solstices, divide the seasons, and build calendars. For agricultural societies, predicting rainy seasons, planting times, and the length of the year could be a matter of survival. Early astronomy was not separate from daily life, ritual, or political power. The sun was both an object of observation and the largest clock in the sky. A solar eclipse is one of the most striking celestial events. When the moon passes between Earth and the sun, daylight may fade, temperatures can fall, and bright stars may appear. Many societies once explained eclipses with stories of creatures swallowing the sun, or with omens of political change. Repeated observation and record-keeping, however, allowed ancient astronomers to recognize cycles. Predicting eclipses became a demonstration that order could be discovered in the sky. Ancient Greek thinkers proposed several different models of the heavens. Aristarchus argued that Earth moved around the sun, but Ptolemy's geocentric model felt more intuitive and was widely used for many centuries. From the ground, Earth seems motionless while the sun appears to cross the sky. Without telescopes or a precise theory of mechanics, proving that Earth itself was moving was extremely difficult. During the Renaissance, Nicholas Copernicus rebuilt the heliocentric model and placed the sun near the center of planetary motion. Johannes Kepler later recognized that planetary orbits are ellipses rather than perfect circles. Galileo Galilei used a telescope to observe the sky and saw sunspots. Their changing shapes and positions showed that the sun was not a perfect, unchanging sphere. Their motion also provided evidence that the sun rotates. Observing the sun through a telescope without a proper filter is extremely dangerous and can cause permanent eye damage. Early observers sometimes projected the sun's image onto a surface instead of looking at it directly. Modern specialized instruments reduce the intensity of the light or allow only a very narrow band of wavelengths to pass. Ordinary sunglasses, photographic film, and improvised materials are not safe for solar observation. Isaac Newton passed sunlight through a prism and showed that white light could be separated into many colors. Joseph von Fraunhofer later mapped the dark lines in the solar spectrum. Gustav Kirchhoff and Robert Bunsen helped explain that elements absorb and emit characteristic wavelengths. Through spectroscopy, humans were able for the first time to determine the composition of the sun without traveling anywhere near it. Helium offers a special example. The element was identified in the spectrum of the sun before it was clearly found on Earth. Its name comes from the Greek word for the sun. Helium was later detected in minerals and natural gas on our planet. This story shows that astronomy does not merely apply knowledge from physics and chemistry. It can also lead to the discovery of new forms of matter. During the 19th century, the source of the sun's energy was a difficult problem. If the sun were powered only by chemical burning, it could not shine for billions of years. Another proposal suggested that the star was slowly contracting under gravity and releasing heat. That mechanism could provide energy for only millions of years, far less than the age of Earth indicated by geology and biological evolution. The development of nuclear physics in the 20th century opened the way to an answer. Arthur Eddington proposed that stars might convert hydrogen into helium. Hans Bethe and other physicists later described the reaction chains in detail. At the same time, understanding the relationship between mass and energy showed that a very small amount of mass could produce an enormous amount of power. The Sun did not need to consume its material rapidly. It could transform hydrogen in its core gradually over billions of years. Cecilia Payne-Gaposchkin used the physics of ionization and spectroscopy to show that stars are made mainly of hydrogen and helium rather than having the same composition as Earth. Her conclusion initially met resistance because it contradicted accepted ideas. It later became a foundation of modern astrophysics. The elements familiar from rocks and living bodies are only minor ingredients in the Sun, while the universe as a whole is dominated by its two lightest elements. The total solar eclipse of 1919 was also used to test a prediction of general relativity. Light from stars passing close to the Sun appeared to be deflected because the Sun's mass curved spacetime. Although the early measurements had limited precision and the test was later repeated with better methods, the event helped bring Albert Einstein's ideas to a wide public audience. During the 20th century, solar observation expanded beyond visible light. Earth's atmosphere blocks most X-rays, ultraviolet radiation, and several other kinds of radiation, a protection that benefits life but limits ground-based telescopes. Rockets, satellites, and spacecraft allowed instruments to operate above the atmosphere. The Sun began to look different at every wavelength. A region dark in visible light might shine strongly in X-rays. A plasma loop almost invisible to the eye could stand out clearly in ultraviolet images. Radio telescopes study radiation produced by electrons moving through magnetic fields and track emissions associated with solar flares. Optical telescopes measure the photosphere, sunspots, velocities, and magnetic fields. Ultraviolet instruments observe the chromosphere, transition region, and corona. X-ray telescopes record extremely hot plasma. Particle detectors sample the solar wind directly as it passes a spacecraft. Each instrument reveals a different part of the same system. The Solar and Heliospheric Observatory, usually called SOHO, was launched in the middle of the 1990s and placed near a point of gravitational balance between Earth and the Sun. From there, it observes the Sun almost continuously, studies the interior through helioseismology, measures the solar wind, and uses coronagraphs to block the bright disk so that the outer atmosphere can be seen. SOHO has also discovered thousands of comets, more than any previous observing program, even though comet hunting was not its primary mission. The stereo spacecraft were sent into different orbits around the Sun so that they could observe it from separated viewpoints. Stereoscopic images allow scientists to study the three-dimensional structure of CMEs and follow them as they move through space. An eruption viewed from Earth can be difficult to place in depth, rather like a cloud moving directly toward an observer. A side view makes it easier to estimate the eruption's speed and direction. HINODE studies solar magnetic fields, the photosphere, and the corona at high resolution. The Solar Dynamics Observatory, usually called SDO, repeatedly images the entire solar disk at many wavelengths and at a rapid cadence. Long sequences of SDO observations allow scientists to follow active regions, waves, flares, and coronal loops over time. The data are scientifically valuable and also produce striking images, in which colors are often assigned artificially to represent wavelengths that human eyes cannot see. Parker's solar probe was designed to travel closer to the Sun than any previous spacecraft. Instead of plunging directly toward the star, it repeatedly flew past Venus to reduce its orbital energy and gradually lower its closest approach. A heat shield facing the Sun protects the instruments behind it from intense radiation. Although the surrounding environment reaches extremely high temperatures, the low particle density and the spacecraft's thermal control design allow it to operate. Parker Solar Probe has entered a region where magnetic fields and plasma remain closely connected to the corona, crossing a boundary commonly called the Alphen critical surface. This is not a visible surface, but a region below which plasma has not yet escaped freely from the Sun, and waves can still travel back toward the star. By directly measuring particles, electric fields, and magnetic fields at close range, the spacecraft helps researchers investigate the origin of the solar wind, the acceleration of particles, and the heating of the corona. One important discovery from measurements close to the Sun is the presence of sudden reversals in the magnetic field, commonly called switchbacks. For a short interval, the field direction bends sharply and then returns. These structures may be connected with energy released from small magnetic regions, plasma motion in the photosphere, or waves traveling outward. Their precise origin and their contribution to the acceleration of the solar wind are still being studied. On June 8, 2026, Parker Solar Probe completed its 28th close approach, once again reaching the record distance of about 6.2 million kilometers from the Sun's surface. These close passes allow the spacecraft to measure the solar wind and atmospheric activity near their source, while also following how the environment around the star changes through its activity cycle. Solar Orbiter combines remote observation with direct measurements of the plasma environment. Repeated flybys of Venus have gradually tilted its orbit away from the plane in which most planets move. In March 2025, the spacecraft recorded the first clear images of the Sun's south polar region from outside the ecliptic plane. This new viewpoint helps scientists study how the polar magnetic field weakens, reverses, and participates in the activity cycle. Solar Orbiter has also photographed many small brightenings in the corona. These are small-scale releases of energy that occur very frequently. If they are numerous enough, they may contribute part of the energy needed to heat the corona. Determining their total energy and physical mechanism, however, requires further observation. On the ground, telescopes such as the Daniel K. Inouye Solar Telescope use large mirrors, adaptive optics, and polarimetric instruments to observe extremely small structures in the photosphere and chromosphere. Earth's atmosphere causes images to shimmer, but adaptive optic systems measure the distortion and adjust mirrors many times each second. The resulting resolution reveals filaments within sunspot penumbra, tiny magnetic features, and plasma motions on scales that were previously impossible to see clearly. To forecast space weather, observatories monitor active regions, measure photospheric magnetic fields, detect X-ray flares, and observe CMS with coronagraphs. Spacecraft positioned between Earth and the Sun measure the solar wind before it reaches the planet, providing warnings ranging from a few tens of minutes to about an hour, depending on the wind's speed. This is a short interval, but it can help operators of satellites, power grids, and aviation systems prepare. Even with large amounts of data, predicting flares and CMEs remains difficult. The three-dimensional magnetic field of the corona cannot yet be measured completely and directly from a distance. Measurements made mainly at the photosphere must be used as input conditions for models. One active region may look complex and store large amounts of energy without erupting immediately, while another changes rapidly. Present forecasts usually estimate probabilities rather than giving a certain time for an event. Studying the Sun also helps us understand other stars. It is the only star whose surface we can observe in detail, whose oscillations we can measure, whose individual spots we can see, and whose wind we can sample directly. Processes learned from the Sun are applied to explain magnetic activity, flares, and winds on distant stars. In return, observations of thousands of stars at different ages allow the Sun to be placed within a broader course of stellar evolution. Some young stars rotate rapidly and produce far stronger flares than the Sun does today. Observing them helps us imagine the environment experienced by the early Earth. Sun-like stars that are older show that rotation and activity decline with time. Stellar winds carry angular momentum away, causing a star's rotation to slow gradually. Because rotation is connected with the dynamo, the magnetic field also changes as the star ages. The Sun is now near the middle of its main sequence lifetime. It has consumed part of the hydrogen in its core, but still has enough fuel for roughly another 5 billion years. This does not mean that conditions on Earth will remain unchanged throughout that time. As hydrogen becomes helium, the number and arrangement of particles in the core change, and gravity causes the core to contract slowly. The contraction raises the temperature and makes fusion proceed more rapidly. The Sun therefore becomes gradually brighter with time. Estimates suggest that the Sun's luminosity increases by about 10% every billion years, although the real change is continuous and the models contain uncertainties. Over a human lifetime, the difference is negligible. On geological timescales, however, it will profoundly affect climate and the survival of liquid water. Models suggest that in roughly a billion years or somewhat longer, a brighter Sun will accelerate the weathering of rocks and remove carbon dioxide from the atmosphere, making photosynthesis increasingly difficult for many plants. Farther in the future, a moist greenhouse state may cause the oceans to lose water gradually. The exact time when Earth will cease to support complex life depends on many factors, including clouds, the carbon cycle, geological activity, and the ability of organisms to adapt. There will be no single day when the planet suddenly changes from habitable to uninhabitable. Different environments will change at different rates. Microbial life in sheltered places may survive longer than ecosystems at the surface. After about 5 billion years, hydrogen in the core will become depleted enough that fusion can no longer provide sufficient energy at the very center. An inert helium core will form and contract, while hydrogen continues to fuse in a shell surrounding it. The increased energy will make the outer layers expand. The Sun will leave the main sequence and become a red giant. During the red giant phase, the Sun's radius will grow by hundreds of times. Mercury will almost certainly be engulfed, and Venus is likely to share the same fate. Earth's future is more complicated. As the Sun loses mass through powerful winds, Earth's orbit will tend to expand, but tidal interactions and drag within the red giant's thin outer atmosphere may pull the planet inward. Models do not fully agree on whether Earth will be swallowed or narrowly escape beyond the edge. Under either scenario, its surface will have become uninhabitable long before then. The sky of an imagined Earth that still existed at that time would look entirely different. A red sun would fill much of the sky, the oceans would be gone, and the surface would be hot enough for rocks to undergo profound change. Yet there is no guarantee that any natural observer would remain there. 5 billion years is longer than the entire present age of Earth. If descendants of life still existed, they would probably have changed beyond recognition or moved to other environments. When the contracting helium core becomes hot enough, helium nuclei begin to fuse into carbon through the triple alpha process. In a star with the Sun's mass, the reaction begins suddenly in an event called the helium flash. Despite the dramatic name, most of the released energy is absorbed within the core and does not blow the star apart. The Sun then enters a shorter period of stability, fusing helium in the core while hydrogen continues to fuse in a surrounding shell. When helium in the core is exhausted, the Sun will expand again and enter the asymptotic giant branch. It will undergo thermal pulses, lose mass rapidly, and blow its outer layers into space. Material enriched with carbon, nitrogen, and other elements will be returned to the interstellar medium. Gas ionized by the exposed hot core may glow as a planetary nebula. The name planetary nebula is a historical inheritance. Through small telescopes, some of these objects look like planetary disks, but they have nothing to do with the formation of planets. They are shells of gas expelled by low and intermediate mass stars near the ends of their lives. Each nebula remains bright for only a relatively short period before its gas expands and blends into the surrounding medium. The remaining core of the Sun will become a white dwarf with roughly half the Sun's present mass compressed into an object about the size of Earth. Matter will be packed to an extraordinary density and supported by electron degeneracy pressure, a quantum mechanical effect. The white dwarf will no longer sustain significant nuclear fusion. It will shine from stored heat and cool gradually over an immense span of time. The Sun is not massive enough to build an iron core or explode as a supernova. It will not become a neutron star or a black hole. By cosmic standards, its ending will be comparatively quiet: expansion, loss of the outer layers, and the survival of a small, hot core. Even so, the process will transform the solar system completely. The remaining planets will move into wider orbits as the Sun loses mass. Comets will be disturbed. The giant planets will grow cold beneath the faint light of the white dwarf. For trillions of years, the white dwarf will continue to cool. The universe is not yet old enough for any white dwarf to have cooled completely into the hypothetical state known as a black dwarf. That final stage therefore exists only in models of the extremely distant future. By then, the Milky Way itself will have changed. Many stars that shine today will have gone dark, and the structure of the galaxy may no longer resemble what we see now. Long before that distant future, however, the Sun still presents many unanswered questions. One of the greatest remains the heating of the corona. Instruments have observed waves moving through the atmosphere, small reconnection events, and turbulent motions in the plasma. Models are becoming increasingly detailed, yet tracing energy from the photosphere into the corona across every scale remains difficult. Structures smaller than the limits of present resolution probably play an important role. The origin of the slow solar wind is also not fully clear. Fast wind is relatively well connected with coronal holes, but slow wind varies in composition and structure. It probably comes from several sources, including the boundaries of open field regions, the tops of magnetic loops, and plasma released by reconnection. Spacecraft passing close to the Sun are attempting to connect the plasma they measure with specific locations on the solar surface. The solar dynamo is another mystery. We know that differential rotation, convection, and large-scale flows all play roles, yet we still cannot predict the strength of every coming cycle with precision. Different models produce different forecasts. Understanding the cycle requires observations of polar magnetic fields, deep flows, and the transport of magnetic flux throughout the convective zone. The solar dynamo is another mystery. We know that differential rotation, convection, and large-scale flows all play roles, yet we still cannot predict the strength of every coming cycle with precision. Different models produce different forecasts. Understanding the cycle requires observations of polar magnetic fields, deep flows, and the transport of magnetic flux throughout the convective zone. Major flares also raise questions about the limits of the Sun's activity. Observations of Sun-like stars show that some produce superflares far more powerful than any event recorded in modern history. Those stars, however, are often younger, rotate faster, or possess different magnetic conditions. Determining how extreme an event the present Sun can produce has direct importance for technology and human spaceflight. Indirect records in tree rings, ice cores, and sediments show that intense bursts of energetic particles occurred in the past. When particles from space strike the atmosphere, they create radioactive isotopes such as carbon-14 and beryllium-10. Unusual peaks in these records probably reflect exceptionally powerful solar events or other cosmic sources. Comparing different isotopes and their dates helps scientists estimate how often such rare events occur. The connection between the Sun and climate also continues to be studied with increasing precision. Satellites measure total solar irradiance, the solar spectrum, and variations through the activity cycle. Climate models examine how small changes in the upper atmosphere can propagate downward. The goal is not to identify a single cause, but to separate the contribution of each influence within a complex system. Even basic quantities, such as the Sun's exact chemical composition, continue to be refined. Modern three-dimensional spectral models produce different estimates from some older models for the abundances of oxygen, carbon, and other heavy elements. These revisions sometimes create tensions with results from helioseismology. Resolving the differences requires better atomic data, more accurate atmospheric models, and perhaps adjustments to models of the solar interior. What humanity knows about the Sun today is the result of centuries of observation, from the first telescopic views of sunspots to neutrino detectors buried deep underground and probes now flying through the corona. No single measurement can tell the whole story. Spectroscopy reveals composition, helioseismology exposes deep structure, neutrinos carry information from the core, and spacecraft sample the wind and magnetic field in space. Taken together, the evidence reveals a star that is stable over billions of years, yet changes from minute to minute through the motion of plasma and magnetic fields. For Earth, the Sun is more than a bright object in the sky. Its light powers photosynthesis, its heat drives the climate and water cycle, and its gravity holds our planet in orbit. The solar wind continually presses against the magnetosphere, sometimes creating auroras, and sometimes disrupting satellites, communications, and power grids. Life exists not because the star is perfectly gentle, but because Earth lies at a suitable distance and possesses an atmosphere and magnetic field that help moderate its influence. When night falls, the Sun does not switch off. Earth has simply rotated our part of the surface away from its light, while a new morning is beginning on the other side of the planet. Deep in the core, hydrogen continues to fuse into helium. In the outer layers, plasma continues to rise, sink, and carry magnetic field lines with it. Farther out, the solar wind keeps flowing across the orbits of the planets, extending the star's influence to the boundary with interstellar space. The Sun is not the center of the universe, nor is it the largest star in the Milky Way. But for the planetary family to which we belong, it is the beginning of every story. From here, the journey will continue to Mercury, the world closest to the Sun, where a small, rocky planet endures intense light, extreme differences in temperature, and a surface covered with the scars of ancient impacts.